掉头了，能进去一点。
Thank you, Mr. Chairman. Before proceeding with the technical talk, I wanted to take just a moment or so to echo some of the comments and sentiments that have been made by other foreign speakers here. This is my first visit to China, and I'm really enjoying it very much here. And I really wanted to congratulate the local organizers, Professor Kim Ming-Zhu in particular, for all the very excellent hospitality we are receiving. The large quantities of high-quality food and other things that we will all be leaving, I think, with some excess weight, not only in our baggages, but also on ourselves. As mentioned, the title of the talk is Optimal Distribution of Catalyst and Pellets. We've been working in this area for some number of years, and the work involves both theoretical aspects and experimental aspects, and I wanted to review some of the results we have gotten to date. The idea of an optimum is very appealing always, to try to do the very best that one can do in experiments and in life. And it's nice to see that it is possible by applying principles of chemical reaction engineering, by taking advantage of the coupled nature of diffusion and reaction that can occur within catalyst pellets, that one can in fact describe an optimum situation that could exist. So the topic being then the optimal distribution of catalyst and pellets. For a fixed total amount of catalyst, how should we go about distributing this catalyst in the pellet in order that we maximize some performance index of the catalyst? This performance index could be reactivity given by effectiveness factor of the catalyst, it could be selectivity, it could be yield, it could be any number of these features. So we want to ask the question, given a fixed amount of catalyst, how to distribute it in a support in order to maximize the performance of the catalyst. Over the years, so this work, as I mentioned, has both theoretical and experimental components. Over the years, we were developing the theory and the experiments side by side. And finally, just recently, a few years ago, we were able to reach a result that is of quite general significance. The result is as follows. And before I give you the result, I should mention that this really truly was an international cooperation in order to achieve this result. The lead author being Hua Wu from China, from the Dalian Institute, who was with us during the time that this work was done. Alina Brunovska from Czechoslovakia, Massimo Morbidelli from Italy, and myself, originally from India, living in the US. So this really was truly a global effort at trying to reach this result of global significance. The result is the following, that we can reach now this conclusion that for any catalyst performance index, it could be effectiveness, selectivity, or yield, and for the most general case of an arbitrary number of reactions, so there could be any number of reactions occurring, and the kinetics, they could be following arbitrary kinetics, all these number of reactions, and they could be occurring either isothermally or non-isothermally in a pellet, which means that there could be either heat effects or no heat effects. And there could be either finite external mass and heat transfer resistances or not. So in general, in the most general situation, the theoretical result is that the optimal catalyst activity distribution, the distribution of the catalyst within the support, is a Dirac delta function. What this means is that to obtain the best performance of the catalyst, you should deposit the catalyst within the support at a very specific radial position within the pellet. And when you do that, you will then get the best out of the catalyst. There is a restriction in this which I should mention, and the restriction is that the surface area of the catalyst, typically we are thinking of rotor metals, platinum, palladium, things of this sort. So as you increase the loading is being increased only to an extent that the surface area is proportional to the loading. If in fact if you go to very excessively high loadings, then you will not have this feature, and then you will have some sort of a saturation. Then it turns out that then the answer becomes numerical in nature, and the answer is that it is basically sort of a distorted Dirac delta function, distorted about the location where the Dirac was supposed to have been located. I should mention here also that the result is that it's a Dirac delta function, but the actual position of the catalyst within the support, in fact, even for everything else being identical, it depends on what the performance index is. So that if you are trying to maximize effectiveness of the catalyst, which is the reactivity, overall activity, then there will be a different location in general. And if you're trying to maximize selectivity, it will be a different location. So the fact that it's a Dirac delta function does not mean that it's the same Dirac delta function for all the performance indexes, even if everything else is the same. But the fact that it's a Dirac delta function is in fact a result of general conclusion. If we go to the next slide, this result says this, so we need to be able to deposit the catalyst then in very specific locations within the support. And here I'm demonstrating for you the experimental method of, to demonstrate experimentally that in fact this can be done. What are shown here are in these dark rings are platinum, and the white part here is a gamma alumina support. So this is platinum distributed on gamma alumina, and what's being shown here then is that it is in fact possible to put the catalyst in very narrow rings, bands within the support. The basic technique of doing this is in fact one that was invented by Michalko in the very early 1960s in a patent in UOP, and it grew out of the very early efforts of automobile exhaust catalysis. We have modified Michalko's technique because he was not interested in his technique to deposit very sharp, narrow bands anywhere at will. So he was simply depositing them very close to the external surface in a band, because he was concerned about the resistance and to save the noble metal from being deactivated due to poisons present in the exhaust stream. So, but in any case, the basic preparation technique for platinum and gamma alumina is essentially a modification of Michalko's technique in which one does a sequential impregnation of the support. So in this case, what one will do is, for gamma alumina, platinum on gamma alumina, one would take gamma alumina and put in a solution of chlorogenic acid for a certain amount of time, at which time then you would have chlorogenic acid on the outer periphery of the support. So if you wish to make then an external shell catalyst, you would then simply take this and dry it and calcine it in order to fix the catalyst in this location. But if you do want to move the ring around, all you do simply is you take this wet catalyst at this stage without fixing it, and then put it in a second solution of citric acid or any other similar acids. Hydrochloric acid is another one that has been used. And what happens then in this case is through a chromatography effect, one basically lifts this band of platinum chlorogenic acid that is adsorbed, and this band is forced inwards, and the citric acid or the hydrochloric acid deposits then in the outer ring, and forcing this chlorogenic acid band to move further inwards. In this process, some of this chlorogenic acid adsorb also moves outward in the solution, in fact, but much of it does move inwards, and the location then of the band is fixed by the concentration of citric acid, the second impregnation, as well as the time of the second impregnation. And what I'm demonstrating here by the first two pictures here is that if I do this second impregnation, the concentration of citric acid being the same in the two experiments, for the duration being in this case 15 minutes, and in this case 60 minutes, that by increasing the second duration, one moves by this chromatography effect the chlorogenic acid ring deeper into the pellet. We can also move it deeper into the pellet by a second effect, which is the same duration of impregnation for the second step, but to increase the concentration instead of citric acid. In this case also it's moved deeper within. What one can also do to change, for example, the loading. So one can move the band at will within the support. By the way, these pellets were 1/8 of an inch diameter pellets. So this whole thing is 1/8 of an inch diameter. So we can move the band at will. Suppose we want to change the loading of the platinum in this case, what do we do? Well, but we want to have the band in the same location but for higher loading. This can be controlled by simply increasing the concentration of chlorhydric acid in the first impregnation step. So what is happening between these? So the first row of pictures and the second row of pictures appear very similar. They are at the same location, the bands. So everything is identical between these rows. The only difference is that the concentration of chlorhydric acid in the first impregnation was double in the second case as opposed to the first case. So one gets the same locations, but a larger loading. In fact, in this case, is twice as much as in the first case. One can also, if one does a co-impregnation of chlorhydric acid and citric acid, one can then make uniform catalysts. So uniform catalysts can be obtained simply by having a co-impregnation of the two solutions. So one has an opportunity then and the possibility of making through a controlled impregnation, sequential impregnation procedure, catalysts in which, at least in the case of platinum and alumina, the ring can be placed at will anywhere one wishes, and the loading can also be changed according to desire. Before I leave this slide, I just wanted to also mention that not only are we able to make these catalysts, we have also developed a whole diffusion absorption theory, a competitive absorption diffusion theory, in order to predict, depending upon the individual absorption parameters, the rates and the capacities for the individual components to be absorbed. We can in fact predict all these things as well. So not only can they be made, but there's also a theory that goes with it, which actually predicts how all of this will occur. I want to now show you some experimental work. There are several I can show at this stage in order to demonstrate to you how people have gone ahead and used the theory to do experimental confirmation of this effect of the optimal distribution of catalysts in the support. And I thought that it would be good to show you here the two experiments that came from Bob Wood's PhD thesis at the Notre Institute here in 1988. In which they studied ethylene hydrogenation of palladium, alumina, and steel methanation of nickel alumina, and demonstrated that if you put the catalyst, the same amount of catalyst being put in different locations, either at point 4, point 8, so on and so forth, that one in fact has a different effectiveness factor for the catalyst, for the performance of the catalyst, a very sharp maximum. So this will then be the optimal location of the catalyst. This fixed amount of catalyst is just being moved around in a band. And this was a mechanically prepared pellet, rather than a pellet prepared by impregnation techniques. In this case, if you put the catalyst essentially on the external surface, one would have one effectiveness factor of essentially 1. So one can increase the activity of the whole pellet now with the catalyst, or the same amount of catalyst, by a factor of 18 by simply properly distributing the catalyst in a sharp band at the location dictated by the theory. And here is a test for the steel methanation of nickel alumina. In this case, by the way, the reaction is very highly exothermic. So when it's although it's positive order in the kinetics of ethylene and hydrogen, it is highly exothermic. So we are taking advantage in this case in the reactivity of a higher temperature at the location of the catalyst, and therefore one gets a very high effectiveness factor, because the catalyst, the temperature where the catalyst is located, since it's inside, that's where the heat is generated. So the catalyst is hot at that stage, it has a higher activity than it would have if it was all on the outside. In this case, the advantage being taken here is of a biomolecular Lambert-Hinshelwood mechanism, in which there is a maximum in the concentration of one of the reactants, which maximizes the rate. So a decreased concentration, in fact, increases the rate. So this is essentially isothermal situation, and here again, the same feature as we see here, that there is a location where the catalyst were deposited all in that location, one would have the maximum possible activity of the catalyst. And in this case, Boyle also did not only the experiment, but also the theoretical comparison to demonstrate that in fact the theory holds very clearly and satisfies the experiment very well. We have the next slide. Very recently, so we have done a number of experiments also, and I thought I should share with you some of our own very recent experiments in this regard. We have been in the last year or so involved with ethylene oxidation on silver catalyst in order to try to make ethylene oxide, this being a very important chemical, as one knows well. In the US itself, this is approximately $2.5 billion industry. So this is a very important key chemical. And so we said, let us investigate in this case for a fixed total amount of silver, how to distribute the silver within an alpha alumina supported pellet so that we can maximize the performance of the catalyst. The experimental conditions are written here. They're typically under the industrial conditions. The only difference is that since we are interested here in demonstrating a fundamental point, we do not have any promoters or any other such things in the gas feed, either in the catalyst or in the gas feed. For example, chlorine is used very much in order to enhance the selectivity of the catalyst, or in solid, in the catalyst itself, along with silver, a large number of promoters, solid promoters, potassium, sodium are used. We do not use any such thing because we want to sort of relatively clean experiment in order to demonstrate simply the effect of the distribution of silver on the alpha alumina support. Although I'm demonstrating the results that I will share with you, are all for the oxygen-rich condition, so that oxygen is in excess and ethylene is being varied. We also have a very similar number of experiments that I won't show you because they simply repeat the same thing on the ethylene-rich regime, which in fact is the industrial regime. Because in between, as you will recall, for the ethylene oxidation, there is a region of flammability. So one does, for productivity, large productivity of ethylene oxide, one actually operates in the ethylene-rich regime in order to have high yield of the product. So we did do the experiment in an external recycle reactor, and we do a single pellet experiment. And if you see the next slide, here is a picture of the pellet itself. It's a single pellet, and it's about 2 centimeters in diameter. And the dark part here is the active catalyst. The light part here is the alpha alumina support. The active catalyst itself is about 33% silver loaded onto alpha alumina support. And this is prepared separately. And then we make the basic inert support, which is this white part, is actually alpha alumina with a certain amount of sodium hydroxide on it in order to decrease its activity for ethylene oxide combustion and the isomerization that can occur of ethylene oxide to acetaldehyde. I guess I still want to do the previous slides. So we can move the band, because this is not now an impregnation strategy, but a layer strategy in which the active layer is being pressed together with the inert layer. So we can move this layer anywhere we wish according to will, and we will see then what the result of this will be. So the same layer is being moved around, the same batch of catalyst active powder is prepared in one shot, and then this will be moved around to see what the result is of this kind of experimental experiment. We now see the next slide. This kind of a pellet, as I mentioned, is a single pellet, and we made a special type of reactor. It's a reactor in which it's a square cross-section for the gases to flow, and the pellet itself is placed in a Teflon cup. There is Teflon tape put around it in order to have good sealing. And the gases flow on the top, and this is the thermocouple that's measuring the gas temperature very close to the pellet itself. So this is that single pellet one of the pellets that I showed you, in the previous slide. So this thing then sits inside this reactor, and there's an external loop in which there is a recycle ratio of approximately 170 or so. So we have extremely well mixed gas phase conditions. So there is so from the fluid mechanics point of view, the fluid phase is completely well mixed. So that the conditions we will see at the exit of the reactor are the same bulk fluid conditions in the reactor itself. So there is no gradient as one is moving along the reactor along over the catalyst pellet, because there is essentially a CSTR, or a continuous stirred tank reactor type of performance. We now see the next slide. I'm just trying to show you something about the experimental setup itself. Here is where the reactor sits, and this is we're looking at the back side. And if we take the next slide, that would be the front side of the setup. So there is mass flow controllers and GC and infrared analyzers to monitor continuously the CO2 coming. So this gives you a view of how the experimental setup is located. If we now look at the next slide, we will actually see some results. I'm only going to show you some very limited number because we can do this for a long time, but the time being limited. What I'm showing is sort of a compressed version of a lot of experiments in terms of the selectivity conversion behavior for this ethylene epoxidation or silver alcohol support. So we are taking now that layer, the active layer, and we are moving this layer around in the pellet, moving it deeper and deeper. So as we move deeper and deeper, we move in this direction, sort of in the wrong direction. So the 0 means that the active layer is right on top of the surface. 0.64 means that the top of this active layer is 0.64 millimeters from the top, and so on and so forth. The conversion is being changed. This is one particular feed, ethylene concentration. The conversion is being changed by a change of temperature. So 210 degrees Celsius are all these left points are all 210 degrees Celsius. And we go in increments of 15 degrees Celsius, so it's 225, 40, 255, 270 for all these experiments. So a large number of experiments can be easily represented in a picture of the sort when we then look at selectivity conversion. And what one sees here is that in fact the best performance is being given when the active layer is right, in this case, on the external surface. To have a better performance, we want to be having high conversion and high selectivity. So you want to be operating as close as possible to the top right-hand corner. So this is the best catalyst, is that put all of the active catalyst in the top surface, and this is the best distribution. If you look at the next slide, another experiment that was of interest is being shown here. What's happening here is that for a given ethylene concentration, we're doing slightly different type of a preparation of the pellet now. And the way this is being prepared is that, so let's start at the top. So all the layers will begin at the top, and the entire pellet is about 4 millimeters thick. So it's about 4 millimeters thick pellet entirely. So we have a certain amount of the active powder, and we have a certain amount of the inert powder. So we can mix them now in different ways. One of the ways we can do it is that we can put all of our inert powder at the bottom and put all the active powder at the top. If we do that, we'll have the active layer thickness of 0.4, and that will be this particular curve here. If we now take approximately half of the inert powder and all of the active powder, mix the two together, we'll still be having half of the inert powder remaining. So we can take that rest of the half of the inert powder remaining and leave it at the bottom, but take this mixture of all the active and half of the inert and start right at the top, and then we'll get this curve. If we take all the inert powder and all the active powder, mix it all together, and press it all together, we will then get this 3.6. We will have a 3.6 millimeter thick pellet, which is uniformly active now because it has all the active and inert powder together. So basically, we are going from an external shell catalyst to a uniform catalyst by simply mixing proper ratios of the inert and the active powder. Now this is a very strong test at this stage because it is the same batch active powder and the same batch inert powder. So we don't have a situation of different dispersions, different crystal planes, or any of the other things that can complicate life in this case. So this is a strong demonstration of the aspect of optimal distribution of the catalyst. So here you see in a very dramatic way, in my view then, that the uniform catalyst is in fact the worst catalyst in this case. And the best distribution is that you put all the catalysts at the top surface. Now this is the case in this particular reaction, but as I have shown you before, in other experiments it will be a different location that will be best. So in this particular case, the surface location of the catalyst is in fact the best. And these improvements that one is seeing in catalyst performance are non-trivial, and I wish to emphasize this. If you take, for example, a 30% conversion, then you can have it with a uniform catalyst at a selectivity of about 40%. Or at the same 30% conversion, you could get a selectivity of around 70%. So for the same amount of catalyst, same conditions for the feed, but of course a different temperature, because the temperature here and here is the same, but here will be different than here. So that for the same 30% conversion, we could be with a uniform catalyst having to get a selectivity only around 40%, but we could then instead get around 70% selectivity. And as you will appreciate in the case of ethylene oxidation, 0.1%, tenth of a percent improvement in selectivity in the US means $1 million per year. So we are really talking about quite non-trivial improvements that can actually occur by the use of proper distribution of the catalyst. I could go on because we have really a large number of experiments that I could show. And in fact, this talk I could have distributed into two parts. I have a whole bunch of slides which I could talk about CO oxidation in a single pellet and in a fixed bed reactor. But the time being limited, but I do hope that you get the point. And the point is that it is in fact possible to take advantage of a proper distribution, physical distribution of the catalyst by taking advantage of the interaction of diffusion and reaction within the support so that significant advantages can occur in catalyst performance. When properly connected with a theoretical description, one can really take advantage of the idea of optimal distribution to have profitable reaction conditions. Thank you very much.
Time is already over, so I just have only one question.
Yeah, well, here in post Korea, I may have missed something in the very beginning. I can see that the second impregnation would push the first one toward the interior. But what keeps the first impregnation from spreading further into the interior? You have a very sharp band. Why doesn't it spread out when you impregnate in the first place?
What do you mean in the very first time only? Okay. Well, it's a limited duration impregnation. So the first impregnation, for example, that we do is approximately 15 minutes. So it was, I think, something like 1/10 of a molar chloropatinic acid, and only 15 minutes. The pellets were taken out in 15 minutes. If you keep them there, of course, then the band will keep on increasing and will keep on sucking the chlorogenic acid from the solution, and the band will keep on increasing in width. So it's a short duration impregnation that does not permit it to move any further. And then, as I mentioned, if you take such a pellet and you dry it and calcine it, then the catalyst is fixed in that location. If you don't, it is still mobile, and by the use of the citric acid, then you can lift up that band and you will move it inwards, because those sites citric acid would much rather sit on those sites and will display simply musical chairs kind of a situation away from the sites, and will sit on it itself.